Imagine finding out that the person who poured the concrete foundation for your house also built the rocket ship in your backyard.
Right, which is already wild.
Yeah, and then realizing they aren't even listed in the public phone book. I mean, today we are looking at a man whose fingerprints are on basically everything, from the smartphone in your pocket to the literal Apollo moon landing. Yet, if you do a search for his name on the internet's biggest encyclopedia, it pulls up a completely blank page.
It's crazy, and it really forces us to confront this uncomfortable truth about the digital age. We operate under this assumption of total digital omniscience.
Right, like Google knows everything.
Exactly. We just think that if someone altered the course of human history, well, the internet has neatly cataloged their entire life story for us.
But it hasn't. Welcome to today's deep dive. We're examining two sources today that sit in such extreme contrast to each other, it almost feels like a glitch in our historical matrix.
Yeah, that's a good way to put it.
Our first source is this brief but incredibly dense biographical entry from the Computer History Museum. It outlines the life of Jay Last. And it's a resume that spans from the absolute birth of Silicon Valley to the first space voyage to the moon, and then all the way back to the preservation of ancient human history.
It is an incredible timeline. And then you look at the second source. You do a Wikipedia search for JT Last. And the result is just a single line of text. Wikipedia does not have an article with this exact name.
It is stunning.
Oh.
I mean, a literal blank page. So our mission today is to uncover this hidden legacy. We want to understand the monumental technological shifts that Jay Last orchestrated.
Right.
And really explore that wild paradox of how a foundational architect of the modern digital world can be practically invisible to the very search engines that his inventions made possible for you and me.
Because to understand the magnitude of that paradox, we have to look at the specific friction of the era he was operating in. The world we live in today, where computing power is cheap and ubiquitous, it's the direct result of a handful of people solving seemingly impossible physics and manufacturing bottlenecks in the late 1950s.
According to the Computer History Museum, Jay Last gets his PhD in physics from MIT, and he immediately goes to work at Shockley Semiconductor Laboratories. So he's working alongside William Shockley, who was a Nobel Prize recipient, the guy who co-invented the transistor.
A literal pioneer.
Right. But then, in 1957, Last becomes one of 8 people who leave Shockley to about her, found a brand new company called Fairchild Semiconductor Corporation. Now, let me push back on this trajectory for a second.
Sure.
If you are a young physicist working for the Nobel laureate who literally invented the foundational piece of modern electronics, you have it made. Why risk it?
It's a huge gamble.
I mean, leaving that lab feels like getting hired to play in the Beatles right as they get famous, only to quit and try to start your own band in a garage somewhere.
Well, you have to separate the theoretical breakthrough from the practical application. Shockley had the Nobel Prize for the concept of the transistor.
Okay.
But taking a concept from a pristine academic laboratory and turning it into something that can be reliably manufactured at scale, that is a totally different sport.
Got it. So the theory was there, but the manufacturing wasn't.
Exactly. The transition from theoretical physics to scalable engineering was hitting massive roadblocks. I mean, the early transistors were incredibly difficult to make. They had terrible failure rates, and they were incredibly fragile.
So Fairchild Semiconductor wasn't just about building another lab. It was about cracking the code on mass production.
Precisely. It was the opposite of a pristine, slow-moving academic environment. At Fairchild, the goal was commercial viability. The source notes that Last worked on developing the first commercial silicon planar transistors. And that word planar is really the hinge upon which the entire modern tech industry swings.
I want to break that down because planar transistor sounds like heavy engineering jargon. Planar implies flat, right?
Yes.
So why is making a transistor flat such a revolutionary breakthrough? Because my understanding of early electronics is that they were these messy, three-dimensional things with wires sticking out everywhere.
Yeah, think about how you build a mountain versus how you pave a road.
Go.
Early transistors were essentially tiny, three-dimensional mountains of conductive material. They had these exposed junctions where the different materials met.
And that exposure was a problem.
A huge problem. Because those critical junctions were exposed to the air, any microscopic piece of dust or just any slight change in humidity could ruin the component.
Wait, really? Just the humidity in the room?
Yeah. The failure rates were astronomical.
So they were trying to mass produce these microscopic mountains, and the environment itself was just destroying them.
Exactly. So the planar process fundamentally changed the geometry. Instead of building up a fragile 3D structure, you do all your chemical processing flat on the surface of a silicon wafer.
Oh, I see.
And the genius part is that you then leave a layer of silicon dioxide, which is essentially high-tech rust over the top of it.
Like a seal.
Yes. That oxide layer acts as a permanent, impenetrable seal. The delicate junctions are no longer exposed to the air. They are protected underneath that flat surface.
Okay, I see the leap here. Once you have a flat, protected surface, my guess is you don't have to hand carve or hand wire every single individual piece anymore.
Right.
It sounds closer to a printing press. You could just stamp out hundreds of these flat, protected components on a single piece of silicon.
That analogy is spot on. It shifted electronics from a handcrafted artisanal process to a batch-manufactured printing process.
Oh.
But Last didn't stop at the planar transistor. The source highlights that he then led the R&D group that produced the very first integrated circuit chips.
So going from a single flat transistor to an entire integrated circuit. Let's unpack the mechanism there. If the planar process allowed you to print a bunch of individual flat transistors on a piece of silicon, what was stopping engineers from building massive computers with them? Why did we need the integrated circuit?
Well, engineers of the era called it the tyranny of numbers.
The tyranny of numbers.
Yeah. Even if you can perfectly manufacture millions of single planar transistors, you still have to physically connect them together to make a computer work. You have to solder a wire from transistor A to transistor B, and then to a resistor, and then to a capacitor.
Oh, geez. Which means if you want a computer complex enough to do advanced calculations, you are looking at thousands, maybe millions of manual solder joints.
Exactly. And every single one of those manual joints is a potential failure point.
Right, human error.
A human error, a weak wire, a bad solder blob. The more complex the machine, the more physically impossible it became to wire it all together without it breaking down constantly. It is like trying to manually operate a telephone switchboard for an entire country using physical cables. Eventually, the sheer number of connections just collapses under its own weight.
So the integrated circuit solves this tyranny of numbers.
Yeah.
Instead of printing individual flat transistors, cutting them up and wiring them together by hand, you're printing the transistors and the metallic wires that connect them all onto the exact same microscopic block of silicon at the same time.
Yes.
You completely eliminate the human hand from the wiring process.
You capture the entire electrical system on one monolithic chip. And the group Last led managed to pull this off. They moved the world from hand-wiring discrete components to photolithographically printing complex circuits. Without that specific mechanical shift, the miniaturization required for personal computers, smartphones, the internet, it simply defies the laws of manufacturing physics.
Which makes that empty search result we talked about even more absurd.
Yeah.
He leads the team that creates the literal building block of the digital age, solves the biggest manufacturing bottleneck in modern history, and he slips through the algorithmic cracks.
It's wild.
And most people would stop there.
Yeah.
But the timeline in our source shows a massive pivot. In 1961, Last leaves Fairchild.
Right. He moves over to Teledyne Inc. He joins Henry Singleton, and he sets up a brand new semiconductor division alongside Gene Horney.
Now, they are developing these complex integrated circuits, but they are no longer just focused on commercial use. The source states they are building for Teledyne Systems programs, and specifically for space and military applications, including providing technology for the first space voyage to the moon. This is just a staggering evolution. I mean, mastering commercial chips is one thing, but a chip sitting inside a desk radio in your living room is a fundamentally different beast than a chip sitting inside a Saturn V rocket.
Oh, completely different.
How do you even begin to make that leap?
Well, you have to look at the environmental extremes. The stakes shift from commercial inconvenience to absolute life-or-death reliability.
Right.
A commercial chip in a radio only has to survive room temperature, and it just sits relatively still. A chip bound for the moon has to survive the violent, bone-rattling G-force of a rocket launch.
Just insane vibration.
Yes, plus the hard vacuum of space, extreme temperature fluctuations, from blistering heat to deep freeze, and intense cosmic radiation.
This circles back perfectly to the integrated circuit solving the tyranny of numbers, doesn't it?
How so?
If you tried to send a computer made of thousands of hand-soldered wires into space, the vibration of the rocket launch alone would snap half of those connections before it even cleared the launch tower.
Exactly. That was the exact physical reality NASA was facing. The integrated circuit was not just a convenient upgrade for the Apollo missions, it was an absolute physical necessity. The solid, monolithic nature of an integrated circuit, where the connections are literally baked into the silicon rather than suspended in the air, is the only way a complex navigation computer survives the violence of escaping Earth's gravity.
That is fascinating.
And last division at Teledyne was tasked with designing these ultra-reliable chips that had zero margin for error. I mean, you cannot send a repair technician 200,000 miles into space to swap out a faulty circuit board.
But what really caught my attention in the source is how his role evolved during this period. By the mid-1970s, he has risen to become Teledyne's vice president for technology. And in that role, he is overseeing the technical interaction of Teledyne's divisions, which totaled over 150 different entities.
Yeah, that number 150 entities represents an entirely different kind of engineering challenge.
It sounds like organizational chaos. I mean, it is one thing to figure out the microscopic physics of a silicon wafer in a lab, but managing 150 distinct technological entities, that is like inventing the combustion engine in your garage and then a few years later suddenly being put in charge of the global supply chain, standardization, and quality control for all automotive parts on Earth.
That's a great comparison.
How does a physicist manage that kind of macro-level bureaucracy?
It requires a shift from microsystems engineering to macrosystems engineering. When you have 150 different divisions, some might be making aerospace components, others military sensors, others communication relays. They often speak entirely different engineering languages.
Right, they have different standards.
Different manufacturing tolerances, entirely different cultures.
They're essentially siloed empires under one corporate umbrella.
Exactly. And overseeing their technical interaction means you have to be the ultimate translator and standardizer. You have to ensure that a technological breakthrough in one division can seamlessly integrate with the hardware of another division.
Which is a massive headache, I'm sure.
Oh, absolutely. It is the physics of large-scale human organization.
So he is coordinating the technological output of an empire.
Yeah.
And doing it so effectively that his work directly enables humanity to walk on the moon. It is the absolute pinnacle of technological achievement. Which brings us to the most surprising part of the timeline. You have helped put humanity on the moon. You have managed the technical output of 150 entities. Where do you go from there? Do you look to Mars? Do you try to build a base on the moon?
Well, the trajectory takes a very sharp turn.
The Computer History Museum notes that after leaving Teledyne, Lasty drastically changes gears. He founds Hillcrest Press, a company dedicated to writing and publishing books dealing with California art, ethnic art, and graphic arts. And then, in 1980, he founds the Archaeological Conservancy, an organization entirely dedicated to saving American archaeological sites.
We go from the absolute cutting edge of the extreme future directly into the dirt of the deep past.
I have to be honest, when I first read this, it gave me whiplash.
I'm not surprised.
The guy who built moon-bound microchips is suddenly publishing art books and digging up ancient historical sites. I really want to challenge this pivot. Is this just the eccentric hobby of a wealthy tech pioneer looking for something to do in retirement? Or is there a genuine intellectual thread connecting planar transistors to ethnic art preservation?
On the surface, it looks like a complete disconnect. But if we dig into how a highly analytical physicist actually processes information, we start to see the outline of a true Renaissance mind. It is all about pattern recognition and a deep fascination with complex layers.
How do layers connect microchips to archaeology?
Think about the planar process and the integrated circuit we just discussed. What is a microchip?
It's a tiny flat circuit.
Right, but it is an exercise in profound microscopic layering. You are taking a raw substrate of silicon, and you are intricately patterning layer upon layer of oxide, metal, and doped silicon to create a complex functional system. To build a chip, you have to possess a mind that is deeply drawn to uncovering, understanding, and manipulating unseen structures.
You have to be obsessed with how things are built from the ground up, layer by layer.
Now apply that exact same mental framework to human history and art. What is an archaeological site? It is quite literally the physical layers of human history built up in the soil over centuries, just waiting to be meticulously uncovered, documented, and understood.
That is an incredible parallel, the methodology of peeling back layers to understand a complex system.
The same goes for the art he was publishing. What is graphic or ethnic art if not the complex layers of human cultural expression over time? The analytical mind required to understand the extreme complexity of a silicon matrix is naturally drawn to the extreme complexity of our own history. It is not an eccentric departure at all. It is the exact same intellectual curiosity applied to a different medium.
From the stars back to the soil. There's this beautiful, almost poetic symmetry to it.
There really is.
It is as if, having secured the technological future of humanity and helped push us out into the cosmos, he felt a profound responsibility to look back down at the Earth and ensure that the physical evidence of where we came from wasn't just paved over by the very modern world he helped build.
It reveals a deeply multifaceted individual who recognized that progress without preservation is fundamentally hollow. He understood that the layers of our past are just as critical to the human story as the layers of silicon that will define our future. The Archaeological Conservancy is really about applying scientific rigor to the act of memory.
We have spent this deep dive tracking a life of staggering human achievement. We are talking about the transition from the theoretical physics of the transistor to the scalable reality of the integrated circuit.
Yep.
We are talking about the macro-level engineering required to coordinate 150 tech entities and equip the Apollo lunar missions. We are talking about a dedicated effort to physically save American archaeological history.
Essentially, the structural foundation of the world you operate in today.
And yet, as our second source so bluntly confirmed, when you type JT Last into the search bar of the world's most comprehensive digital encyclopedia, you get a blank page. The person who poured the concrete foundation and built the rocket ship in the backyard does not have a public listing.
It really challenges the blind faith we put into algorithms and crowdsourced databases,
Oh, completely.
We assume these platforms are meritocratic, that they inherently know what and who is important. But this proves that our digital catalog is remarkably fragile. It easily overlooks the quiet architects, the ones who spent their time actually solving the complex physics and engineering problems in the background, rather than standing in the spotlight.
It forces you to look at the smartphone in your hand or the computer on your desk through a completely different lens. These devices aren't just sleek pieces of magic that appeared out of nowhere. They are the result of incredible friction, brilliant problem solving, and lifetimes of dedicated work by people whose names might not even register on a web search. I want to leave you with a final lingering thought to explore on your own today. We just uncovered how one of the founding minds of the modern semiconductor industry, a man whose technology quite literally helped put humanity on the moon, and who dedicated his later years to saving the physical remnants of our ancient history, managed to slip entirely through the cracks of the digital search engines he helped make possible. If a legacy that massive can be a blank page online, what other world-altering historical contributions are you interacting with every single day that the digital age has completely forgotten to record?